In this lesson, we are going to be continuing number theory for math counts by talking about LCM, GCD, and different type of problems in number theory, and divisibility. So let's get started. So first we're going to start off with divisibility rules. Now let's start with 2. If a number ends, well, let's let our sample number be n. If the number n ends with 2, 4, 6, or 8, six, 8, it's divisible by 2. We notice that every single multiple of 2 is an even number. And if a number ends in 2, 4, 6, or 8, 1, it's even, and it's going to be a multiple of 2. So henceforth, it's divisible by 2 if it ends in 2, 4, 6, or 8. Let's move on to the divisibility rule for 3. The divisibility rule for 3 is if the sum of the digits of n is divisible by 3. Then n is divisible by 3. For example, if I have the number 18, I just need to sum the digits. 1 plus 8, I get 9. 9 is divisible by 3, so we can conclude that 18 is divisible by 3. Let's move on to 4. The divisibility rule for 4 is if the last 2 digits of n what I mean is not we don't check, like, let me give you an example. If I have the number 1, 1, 1, 1, 1, 4, 8, I don't check 4 and 8 separately. I just see the number built by these last 2 digits. So number built by the last 2 digits. So essentially the smaller number that's built by the last 2 digits needs to be divisible by 4. Is divisible by 4. Divisible by 4. Now let's move on to 5. The number ends with 5 or 0. It is divisible by 5. Let's move on to 6. N is divisible by 2 and 3. Seven doesn't really have a divisibility rule, so we move on to 8. The divisibility rule for 8 is not often needed in math counts, but you can go ahead and construct it. The other important divisibility rule we need to know is for 9. And that's if the sum of the digits is divisible by 9. The divisibility rule for 8 isn't really needed, but if you want to go, you can go ahead and construct a divisibility rule for 8. And I'm going to give you a little hint. It involves a similar type of a rule that's for 6. Similar type. I'm going to give you a hint if you want to go in and construct it. So those are the divisibility rules you need to know for math counts. 2, 3, 4, 5, 6, and 9. 7 and 8 are not really important. So, we're done with divisibility rules. Let's move on to LCM. So when finding the LCM of two numbers, you want to go ahead and go for the bigger number. So let's say for finding the LCM of, I'm going to give an example. LCM of 4 and 8. You want to go to 8 and start, like 8 times 1 is 8, and see if this is a multiple of this, and we see that 8 is a multiple of 4, so the LCM of 4 and 8 is just 8. That's an easy way to compute the LCM, is just by looking at the larger number and listing out the multiples. That'll usually get the job done in math counts. We don't like to compute LCMs of super large numbers in math counts. But even if you do, remember the same trick. Go to the largest number there and find the multiples. So I'm going to give an example. 2, 4, 8. Find the LCM. What's the largest number? 8. 8 times 1 is 8. Wow. 8 is our LCM. So this is the really thing you should do, because we don't really need to go ahead, since if 8, we're testing the largest number. Obviously, the answer can't be anything less than 8, because 8 is included. We need to have an answer that's 8 or above. In other words, our answer needs to be n or above n, if assuming n is the greatest number in our list of numbers which we're finding the LCM of. So that's how we find the LCM. Now GCD, greatest common divisor, or greatest common factor, is the same thing. The greatest common divisor, you list out the factors, or GCF, or GCD. Let's say we need the same example of 4 and 8. We just list the factors. So we have 1, 2, 3, no, 4, yes. And the second you hit 2 and 4, or what I'm going to say, the second you hit a value in which the square is equal of a number, like in this case we hit 2, and 2 times 2 is 4. So then we move to 1, and we find 1 times what is equal to 4, and we just list 4, and that's it, we're done. We're going to use a similar strategy with 8. 1, 2, 3, no, 4, yes, we hit. 2 times 4 is 8, and now 1 times x is equal to 8. 1x equals 8. That means 8 is the only thing we have left, and we can see that the greatest common factor is just 4, right? So we GCF, we can use it GCD notation, GCD 4, 8 equals 4. And there's also a similar notation for LCM. You can say LCM of 4 and 8 equals 8. So you have a similar notation for LCM and GCD. Now let's move on to, I said in the beginning of the video that this lesson's also going to cover another type of number 3 problems in math counts, and that is problems involving money and coins. So you have to know United States coins, right? So a penny is 1 cent, right? So 1 cent. A nickel is 5. A dime is 10. And then a quarter is 25 cents. We don't really use half dollars in math counts, so you can forget about the half dollars really. But these are the coins you'll be using in math counts. This is a penny, this is a nickel, this is a dime, this is a quarter. A quarter is easy to remember since 25 quarter, quarter of 100. Pretty easy to remember. Pennies, 1, nickel, 5, nickel and dime. You probably should know this is basic math, but this is just a quick review if you somehow don't know this. So, let's move on to the problems. Hopefully you understand all the material here. If you don't, feel free to ask in the comment section below what questions you are having. So, let's get into the problems. What is the remainder when 1,493,824 is divided by 4? So there's two ways to do this problem. One way is just to do 1,493,824 divided by 4, which would take forever, or remainder. Now let's see if this number is divisible by 4, because if it's divisible by 4, the remainder is just 0. Let's look at the last two digits. We remember 4, number built by the last two digits of n, is divisible by 4. We have a number here built by the last two digits. We have 24, which is built by the last two digits. Look at 24. 24 is divisible by 4. 4 times 6 is 24. Obviously, it's divisible by 24. So we know that if it's perfectly divisible, the remainder is going to be 0. So our answer is 0, and we can move on. 11 coins equals 59 cents. How many of these coins are quarters? Now this is the type of the problems involving coins and money. How many of these coins are quarters? Well, it could be 0. It also could be something greater than 0. We have 59 cents. If we get these 59 cents down to 55 cents, that's a multiple of 5, we can use some nickels. So let's just do just that. We have 59. To get to 55, we subtract off 4. So let's place down 4 pennies. So I have 4 pennies down, 7 coins left. Now, how many of these coins are quarters? We have 7 coins left. We could use some dimes. Right now we're at 4 cents. We need to get to 59 cents. We could use a big boost by using a quarter. 25 cents. So we use a quarter just to do a test. We're just guessing right now. And now we have 29 cents and we have 6 left. So now we have 6 coins left. We have 25, 6 coins that we can use. Now our total is currently 29. And we need to get to 59. Now we could use some dimes, 29, 39, 49, 59. So we use some dimes. 29, 39, 49, that's 3 dimes. And we have 30 plus 25, 30 plus 25, 55 plus 4 is 59. We got to our 59 cents, but we have 11 coins. Let's check how many coins we have. 1, 2, 3, 4, 5, 6, 7, 8. We're 3 coins short. So we might be able to use some dimes, but we can't use 3 dimes. We're going to have to get from 29 to 59 another way. Let's think. The difference is 30. Now 30 is a multiple of 5, and it's a multiple of 10. We could mix nickels and dimes, or we could try only nickels. 5 times 6 is 30. We have 6 coins left. So we can use all nickels. let's try that. 5 and then 5. Essentially, we want 6 nickels for this. Each nickel is worth 5 cents. Another 5 cents. And we seem to be done. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 coins equals 59 cents. Let's see if we are equals 59 cents. This build, well, first we're going to have this. We're going to have 1, 2, 3, 4, 5, 6. 5 times 6 is 30 plus 25 plus 4. It's 30 plus 25. That's 55. 55 plus 4. 55 plus 4, that's 59. So we see that we use 1/4, and we see that one of the coins are quarters. So we're done with this problem right here. Let's move on to the next problem. Again, a math counts problem. The least common multiple of x, 10, and 14 is 70. What is the greatest possible value of x? Again, we're searching for the greatest possible value of x. Currently, the LCM of 10 and 14 is some number. Notice how the LCM of 10 and 14, let's find some multiples of 14. 14 times 2 is 28, 42, 56, 70. 70 is a multiple of 10. So LCM of 10 and 14 is 70. Now we need to add another number here, x. Where is the greatest possible value of x? Obviously, x cannot be over 70, but notice how x can be 70. If x is 70, then 70 times 1 is 70, and the LCM remains constant. So the greatest possible value of x is 70. We're down to our last problem. What is the sum of the greatest common factor of 3 and 6 and the least common multiple of 3 and 6? The greatest common factor of 3 and 6 and the least common multiple of 3 and 6. Let's compute the least common multiple of 3 and 6. And we can do this using our trick. 6 first multiple is a multiple of 3. So the LCM of 3 and 6 is simply 6. Now we go to the GCD or GCF of 3 and 6. The greatest common factor, we find that 1, 3, or its factors, and then 6, we have 1, 2, 3. The greatest common factor is 3. So now we have 6 plus 3, the sum with the greatest common factor of 3 and 6 and the least common multiple of 3 and 6 is 6 plus 3, which is 9. So we're done with all 4 problems. And we've used some strategies that we've learned throughout the lesson. We've used GCD. We've used the LCM trick, which is finding the multiples of a larger number and seeing if it's a multiple of a smaller number. And we've also used some tricks for the problem involving coins, where we use guess and check, which is often a great strategy in number theory problems. So hopefully this video is helpful, and yeah, that's lesson 4 of Math Counts Preparation.